Okay, we're going to go a little out of order with today's lesson. We're going to start out by going over the homework. And what you'll notice is I have worked out every single problem on the homework. So yesterday we talked about a method of solving exponential equations. That method was to rewrite both sides using like bases. So when that is a possibility, that is the best way to go. It's the quickest, easiest, simplest way to solve an exponential equation. It's not always possible, but when it is, that's what we should do. So if we look at number 1, we have 110, so the common base is 10. So the left side we'll rewrite as 10 squared. Now make sure, like we stressed yesterday, that when you do that, you are not changing the value. 10 squared is 100. We did not change the value. If you notice that you have changed the value, then you have done something wrong. So make sure you don't get caught with that. All right. So take a look at number 1, take a look at number 2, make any corrections you need to make, and when you're ready, you can press play after pausing and move on. All right, here are 3, 4, 5, 6, 7, and 8. Most of these are fairly straightforward. I don't see any big surprises on these. So go ahead and make your corrections. Make sure you're making corrections, not just marking right or wrong. And when you're ready to move on, press play. All right, I want to talk about a couple of these. Definitely number 14. I want to talk about number 14 real quick. So if we look at number 14, anytime we have a 1 on this side, there's no way I can write 1 to a power and create 4. 1 to any power is still 1. So our little trick about trying to rewrite with a smaller number doesn't work here. So we have to think, okay, my only other base is 4. Is there a way I can represent 4 to a power so that it equals 1? Yes. Any number other than 0 to the 0 power is 1. So when you have a 1 on this side, that's what you're looking. No matter what your base is on the other side, if it's equivalent to 1, it's going to be that base to the 0 power. And then once you do that, you solve. The other problem I wanted to take note of is number 11. All right, so 225 is 15 squared. Now this was 15 to the understood first power. So when we get here, we have 2x equals 1, so x equals 1/2. I want to tie that back into what we talked about last week. 1/2 power. The 1/2 power means square root. Is the square root of 225 15? Yes, it is. So I want you to think about those things. It might be something that you could look at the problem and just know the answer, especially if it's one of those roots that we've studied. All right, so if you have any other questions after correcting these, please ask for help. All right, the next thing is today's warm-up. I want you to go ahead and press pause and try the warm-up. And when you are ready, press play. Okay, so when we're looking at these, it asks us in number 13, first it tells us C is the intersection of AD and BE. If it can be determined, what is the measure of BAC? So BAC is this angle here. So if this is 45, this is 45, because vertical angles are congruent. So then when we add these two, that gives us 80. And with this triangle BAC, we know it must add up to 180. So the answer to number 13 is B. Okay? This one. The central angles are not quite right here, and that's what the paragraph tells us. So if we add up the time, 4, 7, 8, 9 hours. 9 hours, all right? But we're looking at just our core subjects, so that would be 4 out of 9 hours. What does that relate to out of a circle? Well, a circle is 360 degrees, so you can cross multiply and solve, or if you just notice that, hey, if I multiply 9 times 40, I get 360. So 4 times 40 is 160. Your answer is H. All right, number 15. Number 15, the answer is B. Okay, so this month, Cami sold 70 figurines in 2 sizes. The large figurines sold for $12 each, the small for $8. So what do we have going on here? We can let X be small and Y be large, and the total is 70. We have large for $12 and small for $8. And it says the amount of money he received from the sales of the large figurines was equal to the amount of money he received in sales from the small figurines. Okay. So how many large figurines did he sell? So what can we do with this equation at this point? We know that the small money is equal to the large money. And then we could just use substitution. And we want to know large, so we would solve for y. So we would get 8 equals 70 minus x. Minus y. Because if we solve this, we'd have 70 minus y. And we substitute that in. Okay, so we have 8 times 70, which is 560. So 560 minus 8y equals 12. So 560 equals 20y, and therefore 28 equals y. 28 large figures. Now, you didn't have to set up a system. You could have done guess and check because all the answers are there. You might have another quicker way to do that problem also, but that's a way to do it algebraically. All right, let's take a look at today's lesson. Okay, if you did not pick up a note sheet on the way in, these are today's notes. Go grab them before we take today's notes. All right, this one, how do you find the inverse of a function? Well, to find the inverse of a function, we switch the x and y, we solve for y. So in this case, we would subtract the 4, we would divide by the 3, and this gives us the inverse. So the inverse of a function is where we switch the x and y, and we solve for y, and we can use a little inverse notation. So a logarithmic function is the inverse of an exponential function. A logarithm is helpful in so many different ways. We've already learned how to solve equations like this. 2 to the x plus 4 equals 8 to the x minus 1. We know how to do that. We can write them both with the same base and solve. A log comes in handy when we have something that we can't write with a common base. So if we had 2 to the 5th equals 5, we know it's a little bit more than 2, and it's less than 3, and it's closer to 2 than it is to 3, but we don't know exactly where it is. We're just kind of guessing. So what we're going to do today is we're going to learn about logarithm. And what a logarithm does is it solves for the exponent. All right, so if we have an equation that's in exponential form, a base raised to an exponent equals an answer. And I do like to do it like that. A base raised to an exponent equals an answer. So when we don't know what x is and we can't write it with a common base, how can we solve? And so what we use in that case is a logarithm. So how does this switch forms? It does like this. It becomes log. Your base goes here. Your answer goes here. And a logarithm solves for the exponent. So when we get problems like this that we don't know what to do with, we don't know what power to raise 2 to get 5. We have to use a logarithm. So it becomes log. Your base is 2. Your answer is 5. And now we have solved for the exponent. I want to be very particular about where things go here. When I write a logarithm, that's not a straight line at all, but let me move it a little bit and see if I can straighten it out some. Okay, so when we write a logarithm, I want you to notice what sits on the line. The log, the 5, the equals, and the x. So all of that goes on the same line. The base is a subscript. So make sure when you're switching forms that it's very easy to identify the base as a subscript. Okay, so what we're going to practice today is switching back and forth. Logs are new. And when we do new things, sometimes it takes a little while for our brain to completely adjust to them. So today is not difficult, but it is new. So in this first example, it asks us to write this in log form. We know that 2 to the third is 8, so we're about to write a true log statement. It becomes log, your base, because the base is the subscript. The base is 2. Log base 2, the answer part is 8, and it always equals the exponent. So 2 to the third equals x. This is exponential form. This is logarithmic form. So example 2 asks us to go the other way. If it's log base 3 of 81 equals 4, let's write that in exponential form. So in exponential form, we always go base to the exponent equals the answer. So in log form, the base can be found here. So our base is 3. A log always solves for the exponent. So there's our exponent. 4 equals the answer. The answer part is here for the logarithm, 81. Okay, so take just a minute and I want you to rewrite these in the forms, and when you're ready to check your answers, press play. All right, this one is in logarithmic form. It asks us to put it in exponential form. My base is 5, my exponent is 2, my answer is 25. This is in exponential form. It asks for logarithmic form, so it's log, the base is the subscript, log base 4 of 64, because the answer part goes next. And a logarithm always equals an exponent. Log base 4 of 64 is 3. Okay. When we think about logs, we can have them in any base, really, any positive base. But log base 10 is one that we use a lot. Our numbers are in base 10. So log base 10 is called the common log. So if you see an expression in the form log of a number, and there's no base, it is understood to be base 10. So if you see like log of 7, and there's no base here, that is an understood base 10. All right, now, the log button that you see on the calculator is in base 10. For example 3, we're going to rewrite these in exponential form. So there's no number written here. It's base 10. 10 squared equals 100. Base, understood 10, exponent 2, answer 3. Base is an understood 10, exponent 1, answer 10. That makes sense. 10 to the first is 10. 10 squared is 100. All right, no subscript. So it's base 10 of negative 4. There's our exponent. A logarithm always equals the exponent. And the answer part is 1/10,000. Well, that makes sense too, because the negative means reciprocal, and 10 to the fourth power is a 1 with 4 zeros. All right, now we're to rewrite these in log form. So this is log base 10, which we don't need to write, of 1,000 equals 3. This is log base 10 of 100 equals negative 2. This is log base 10 of 100,000 equals 5. So when it's base 10, there's no need to write the 10. Okay, so we've noticed, and I've said it over and over again, that a logarithm equals the exponent. It solves for the exponent. So if you're asked to evaluate a log, you are solving for the exponent. 9 to what power is 6,561? Well, without this handy dandy chart, I might not know, but the chart's right there, so it's the fourth power. So in this case, it is 4. This is equal to 4. Okay, let's do this one. 5 to what power is 0.2? Okay, 0.2 is 2/10. So I'm going to write it like that, 2/10. Oh, well now that I see it like this, 2/10 simplifies to 1/5. So what power do I raise 5 to get 1/5? Negative 1. So log base 5 of 0.2 equals negative 1. So this helps us to evaluate logs without using a calculator. So if we look down here, log base 10. Well, when it's base 10, we can count the zeros. 1, 2, 3, 4. Okay, log base 4 of 64 equals what exponent? And you know what? If you need to write equals x and switch to exponential form to see what's going on, do it. Now we can clearly see that x is 3. Okay, here, if you need to write equals x and switch forms, base raised to an exponent equals an answer. Well, any number to what power? Any number to the 0 power equals 1. All right, let's do this last one. 4 to what power is 1/16? Base, exponent, answer. So, I can see it. Negative flips it, 2 squares it, -2. All right, the last section of notes today. We are switching forms. So first thing we do, switch it exponential. Second thing we do, solve. So this is sneaky. Look how this one, the exponent comes first. A logarithm always equals an exponent, whether it comes first or last. So we know it is n to the -2nd equals 100th. What number can I square and flip to get 100th? 10. Okay, the next one, base. Logarithm always equals the exponent. 2 to the 5th. Use your table if you need to, but the answer is 32. Okay, this is understood base 10, so if you need to write it, write it. 10 to the exponent. Logarithm equals the exponent. So n is 1, 2, 3, 3 zeros. All right, here's my exponent. So the base raised to the exponent equals the answer. It's negative, so it's 1 over, and 5 to the 4th, you can use your table if you need to, is 625. All right, switch forms. This one gave me the log first, so that's what I'm used to. Base to an exponent equals an answer. Use your table if you need to. What number to the 3rd power is 729? The answer is 9. Okay, this one. 15 to the n equals 225. Base, exponent, answer. Whoops, to the n, sorry. So, what power do we raise 15 to get 225? We used that one yesterday on one of our worksheets. If you square 15, you get 225. Okay, so now it's time, once you have your completed note sheet, take your completed note sheet up to show Miss Willoughby, and you can grab your homework. If you have any other questions, make sure you ask before you leave class.